Today I'm going to actually talk about top quark physics, but I would be a lot slower than yesterday because I have very few slides. I have very few topics to share with you, and I would encourage you to stop me as much as possible. I don't guarantee that I'll be able to answer all your questions, but I think we will be able to find the answer before the workshop or the school is over. So today actually we are going to talk about this particle, the top quark, which is one of the 6 quarks present in the particle spectrum of the Standard Model. It's a fermion. It has fractional charge plus 2/3 electric charge. It is charged under color, so there are 3 colors they come in. And they're in the weak interaction, the left and the right-handed partners of the top quark, they participate differently. So the left-handed is a part of the doublet Su2, and it's a singlet. So this is actually true, this information, for almost all the quarks. The first time basically you notice a difference, that how top quark is different from the other quarks, is that its mass is much larger than all the other fermions that you have in this Standard Model. So this is basically the heaviest particles that we have in the Standard Model. And the particle was discovered in 1995 at Tevatron. So as we discussed yesterday also, that in a Standard Model, the same Higgs doublet is responsible or can help you generate the masses without breaking the gauge invariance for the fermions as well. So the Yukawa coupling is related to the mass of the fermion, and for the case of top quark, this Yukawa coupling is of order 1. So what it means that as far as the top quark is concerned, its mass is actually the most natural among all the fermion masses, because its mass is very close to the symmetry breaking scale. That's what basically the naturalness is, that all the scales in your theory should be basically close to the symmetry breaking scale. And this is what is actually related also to the hierarchy problem, that then why all the other fermions have so less mass, because if they are also generated from the same symmetry breaking mechanism. So that's a different thing. The other special thing about this top quark, it decays actually very quickly, because its decay width is quite large. So the time scale associated with this decay is 10 to the power minus 25 seconds. While the other scale that would come in picture is basically the hadronization scale, the time scale associated with lambda QCD 10 to the power minus 24. So comparing these 2 time scales, what we learn that the top quark actually decays before it hadronizes. So there is no actually top anti-top top flavored hadrons actually they are there and there, because it has already decayed before something like this can happen. Because of its very strong, very large mass and strong Yukawa coupling, it plays a very important role in the Higgs physics. Particularly, we have seen it yesterday, that it governs the Higgs production and the decay modes of the Higgs boson. So these are the couplings through which actually top quark interacts with the other particles, for example, with the gluons, with the photon, with the Z, the W, and the Higgs. So this is the most important coupling, because it is of the order of 1, and one is interested in knowing more precisely this coupling, because that's what is related also to the knowing the Higgs boson better. And the main important coupling that we will be focusing today, or that will play an important role, is basically its coupling with the W and the B, which is a charged current coupling. It's of V minus A type coupling. So that means both the top and the bottom, they are left-handed. So let's actually first look at the decay width of the top quark. So since the mass of the top quark is larger than the W boson mass, it can decay into W bosons in this mode. T goes to B into W. And its decay width, you can actually do the QCD correction as well. And what you get basically is decay width for 173 GeV top mass is about 0.3 GeV, okay? And you can do the computation, in your lifetime you get something like this. So the fact that it actually decays very quickly before it hadronizes, that also is related to the fact that the difference between the top quark mass and the W mass is quite large, is of the order of 90 GeV. So that allows basically a large phase. So it decays very quickly. So since the top quark which participates in the weak interaction is left-handed, and as a decay product we get W boson, and W boson is a spin 1 particle. So you can ask this question, that what is the polarization state of this W boson which has decayed, into which the top has decayed. And this question we can ask because of the same reason, that since the decay of the top quark is happening very fast, it is not affected by the hadronization process. So the spin information on the polarization information of the top quark is directly transferred to its decay product. So you can look at the final state decay particles of say W also in say the electronic decay modes, and you can get the information of the top polarization. So here basically the quantity basically which we can which is very useful to understand that what are the possibilities for W polarization in the top decay is you can construct these ratios, which are basically partial decay width for top decaying into say longitudinal W or left-handed W, left-handed, or the negative helicity W, right-handed, or the positive helicity W, divided by their sum. So as you can see, the top quark actually almost most of the time it decays into the longitudinal W boson, the longitudinal W boson, and partially into the left-handed or the negative helicity. And this is actually not difficult to understand, because if you go to the rest frame of the top quark, then your W and B quark, they are back to back. Take B quark to be like massless. So this is actually always left-handed, right? So left for the massless particle, left-handed is basically like a negative helicity. So you can demand now the helicity conservation, and you can show that the only possibilities for the W is that either it's 0 or -1. +1 is actually not allowed by the helicity conservation. So this feature is very important, because if your TWB vertex is modified, then you can expect these numbers to change. So from that point of view, or from the new physics point of view, you would like to know this observable or these numbers very precisely. So currently, basically, at next to leading order, these numbers are given here, like F0 is something like 68%, FL is 31%. You can compare with the case where MB is equal to 0. And since MB is not equal to 0, there is a finite, small possibility that W can indeed go into the right-handed polarization state, but that is actually super small. So the question is basically, how do we get the information on the W polarization? And for that, all we need to do, we need to basically focus on the final state decay particles. Say, for example, you have charged leptons into which W decays. Then this angular distribution, it can be basically expressed in terms of these three quantities, F0, FL, FR. So if you know basically these information, so if you know basically this angular distribution, from here you can just extract F0, FL, and FR. That's how basically, where this theta star is just the angle between the reverse momentum of decaying top and the direction of the charged lepton into which the W decays. But this angle is calculated in the rest frame of the W boson. Okay, very good. So let's actually, since we have learned about the top decay, let's talk about actually what are the top production modes. And the first production mode that we are interested in is the TT bar. So the TT bar production mode is dominated by QCD processes. For example, we have QQ initiated process and we have glue initiated processes. At leading order, its cross section is dominated by the gluon fusion. So for example, at the LSC, if you compute the cross section, you will find that the gluon fusion channel, it dominates the cross section by 90%. So now the higher order corrections are also available for this process, and at present actually at the inclusive level for the 13 TeV LSC, the cross section is something like 816 picobarn, which is huge. Okay. At the inclusive level now, since the data has been collected for both at the Tevatron, at the LSC, and some other actually experiments, so you can ask this question that how well the theoretical predictions agree with the experimental measurements, and they actually, at the inclusive level, the agreement is actually pretty well. So since if we talk about actually next to leading order QCD correction at the differential level, what we can see that at the differential level, the effect of QCD correction is actually quite large. In fact, in certain bins, for example, here in the difference of the rapidities for the top and anti-top, you can see that in the central rapidity region, the QCD corrections can be of the order of 40%. So it is important that you, for a precise prediction of in the TT bar production mode, you do consider basically higher order QCD corrections. The other plot basically which I am showing you, that is related to the best calculation which is presently available, and that is fixed order next to leading order calculation plus the resummed large logs here. And this calculation basically has shown, and it is important in the case when the invariant mass of your top and anti-top is very large, because in that region it has been shown that compared to the fixed order correction, the fixed order next to leading order correction corrected by the resummation has better, has actually, the scale variation is actually more uniform in this case compared to when you just use the fixed order next to leading order corrections. So this is actually important because if you're looking for new physics in the boosted regime, then you need to actually worry about whether your prediction is precise enough or not. Okay. Okay. So related to TT bar production, actually there are many observables that you can construct, and like the W polarization, here you can actually construct observables which are constructed out of the 4 momenta of the decay products of top quark. And you can ask this question that what is the prediction for such observables in this standard model. So I hope you remember, for example, this famous asymmetry observable which is known as forward-backward asymmetry, right? Which you have seen at E plus E minus collider, E plus E minus to mu plus mu minus. And there basically what you learned for the forward-backward asymmetry, that by measuring that you can show that the weak interaction is of the nature of V minus A rather than, so you have QED interaction, you have electroweak interaction, and the electroweak interaction tells you that there is a non-zero forward-backward asymmetry, right? Because you look for the muon in the forward direction and in the backward direction, and because of V minus A, there is a difference. So similarly, at the Tevatron, you have actually PP bar, and since you have asymmetric initial state, you can again ask you can always specify what is your forward direction, what is your backward direction. And in that case, you can define this forward-backward asymmetry in a similar fashion, that you ask that how many of them are in the forward direction or how many of them in the backward direction, just take the difference and the sum and take the ratio. So the situation is basically something like this. So if you can define basically the forward-backward direction, then you can expect basically some of the particles to go into the forward direction and some to in the backward direction. There is asymmetry, and you expect some non-zero result. But at the LSC, something actually different happened because your initial states are proton-proton. So you don't know actually what is the forward direction. But what you can actually notice that in QQ bar to TT bar at the LSC, the quark Q always actually is a valence quark. And valence quark, they always carry the good share of longitudinal momenta from the proton compared to the C quarks. So there is basically the top quark which is produced at the LSC, this is always actually boosted in the forward direction. So your situation is something like this, that your top is boosted along the forward direction while compared to the anti-top. And this is always the case, independent of whether the quark is coming from the left proton or the right proton. If it is coming from the left proton, it will be boosted along the left direction, right? The top will always be boosted along the left. And if it is coming from the right, then it will be boosted along. So your situation compared to Tevatron is something like this, okay? And you can actually utilize this feature to construct a symmetry observable, which is known as charge asymmetry observable. So because actually, as I told you, at the LSC, the cross-section is dominated by the gluon fusion, which is charge symmetric. So you expect that this quantity is not actually very large because it's dominated by the gluon fusion. So this standard model prediction, which is calculated at next to leading order QCD and electroweak level, is really small compared to this forward-backward asymmetry at the Tevatron. Okay? And this, as I said, it is due to the fact that the cross-section is dominated by the gluon fusion channel, which is a charge symmetric production channel rather than QQ bar production channel. Okay, so once again, you can, since we have seen that because of the quick decay of the top quark, the spin information is carried by its decay products. In the TT bar case, what you can ask the question that what is the correlation between the spin correlation between top and anti-top. Okay, so this correlation, because of the fact that it doesn't actually heteronize and it decays actually very quickly. This spin correlation between the top and anti-top is transferred to the angular correlation between the final state decay particles. So for example, consider that your top is decaying into BW and T bar into B bar W minus, then and W further decays into leptonic modes. So by looking at the angular distribution or angular correlation between the charged leptons, you can obtain the information that how the spin of the top and anti-top, they are correlated. Okay. So for example, this is the angular distribution between the final state charged leptons in this case, and this quantity here A is basically, you can actually interpret this quantity A as the quantity which has the information of spin correlation between top and anti-top. So what is important that when you produce TT bar, since it's an spin half particle, it can be actually in two states, right? It can, at threshold, it can be in a spin, it can be a triplet state or it can be actually singlet state. So you can actually see, if you look at the leading order diagrams, then since in the quark anti-quark fusion, it is created via S channel through the gluons. So that means basically it is in the spin 1 state, right? While when it is actually produced in the gluonic fusion channel, then it is spin 0 state. So this information is very useful because if you have some colored scalars, then in that case, the QQ bar channel will give you TT bar in the spin 0 state. So this asymmetry observable, which is constructed, this spin, this asymmetry which has the information of the spin correlation, it can be basically utilized to probe BSM in the production mechanism. So the standard model, its prediction is 0.031 with 1% theoretical error on it. And so this quantity A, which is appearing in the angular distribution, is nothing but how your top and anti-top, how their actually spin is aligned. So what you are saying basically that this N is number of top and anti-top events where both are actually in the spin up state, their spin down state, compared to the cases where top and anti-top, they are spin up or spin down state. So that's what actually this observable is. So let's move to the second top production mode, which is the single top production mode. This production mode is important because it can actually give you an information. It is directly sensitive to the CKM coefficient VTB, right? So there are actually three main production channels through which you can produce a single top. There is a S channel mediated by the W. There is a T channel mediated by the W, and there is the associated production of top with the W. So among all these production channels, the T channel mediated W boson process has the largest cross section. Its cross section is about 1/3 of the pair production cross section, which we have seen something like 900 picobarn. So by studying this process, there are actually many beyond the standard model models where where people expect basically something like W, the W prime bosons can be there. So studying this process, you can basically learn about W prime boson as well. So here is the inclusive cross-section theoretical prediction, which is at present available in the S channel at an NLO level. And as you can see, at the NLO level, the cross-section increases by 35%, while the NNLO effect, they are of the order of 7%. You can use this information on the measurement of the inclusive cross-section for the single top, which is actually displayed in this plot here as well. You can obtain the information on VTB, and currently measured value of VTB from the measurement of the inclusive cross-section is something like 1.05, which is consistent with errors, which is consistent with the standard model value, which is very close to 1. So let's look at these corrections at differential distribution level. So here on the left-hand side, you see the PT distribution of the top quark, which is given at LO, NLO, and next to leading order. So we saw at the inclusive level, the corrections were of the order of 7%, but at the differential level, your corrections can be as large in certain kinematic region as 10%. And what we also can see by looking at the red and the yellow bands here, that these are basically an NLO prediction for two different scales. So meaning that by including the next to leading order correction, the scale variation is also not very large. They are actually very much overlapping. So there is not actually much scale variation once you include next to leading order corrections. The same thing is actually displayed here for the rapidity of the top quark. Okay, so apart from actually these two production channels, which is TT bar and single top production, there are actually many other production channels where top is actually produced. For example, we have already seen the example where top can be produced in association with the Higgs boson. This channel will provide you information on the magnitude of the top Yukawa coupling, which you are interested in. And similarly, you can talk about basically the production of top anti-top in association with the vector bosons. And they provide actually information on, for example, if you want to learn really that whether the charge of the top quark is plus 2/3, this is basically you would like to study this process TT bar gamma, because this is where basically it enters, and that's the only structure there. Similarly, to probe the coupling of the top with the Z boson and the W boson, one would be interested to study the processes TTZ and TTW. And some of these actually processes has already been observed at the experiments. And for example, this process, which is important from the point of view that this is the top production, single top production in association with the Higgs. This process can provide you information on the sign of the top Yukawa coupling. So because of that, actually, it's very important. Currently, it has been observed along with the TT bar Higgs, not actually exclusively, but hopefully in near future when more data comes, we would be able to observe this separately. Okay, this is actually last thing which I want to talk about. I just want to actually mention that in all these predictions, the top quark mass, knowing actually top quark mass is very important, because if you know all the parameters of the standard model precisely, it simply means that you have less theoretical uncertainty. But for the top, it has actually, there is a special situation, because the top, because of its large mass, it affects the running of the quartic coupling very heavily. So if you look at this expression, which is the RG equation for the running of quartic coupling, then it depends upon the top Yukawa coupling as fourth power. So what it means, and there are basically plus and minus signs. So you have to actually worry about that if there are contributions which drive your coupling to the negative value, then you will be in trouble. So the here, for example, in this plot, what you can see that the lambda, it basically depends upon three parameters: the mass of the Higgs boson, the alpha s, and the m top. And if you look at the uncertainty in the m top, that is actually, that creates very different running for the lambda. Okay, so and that is due to the fact that the dependence on the top Yukawa coupling of this running is really large. What is the actually, so the problem is that if you hit the negative lambda, your potential actually becomes, it's not actually bounded from below, right? And you don't want such a potential to work with. So,
from the left side of the figure, how can I see the metastable?
From the left one?
Yeah.
So from the left one, basically you see just the fact that with the lambda is actually, up to what scale lambda is positive or it is negative. That's the only thing actually you see. So metastable would be actually somewhere here, right? I mean, that is not negative, like it's. So you can actually, so for example, in this plot, you can see that if you vary the top quark mass and the Higgs mass, then these three regions, they tell you basically that in, so I mean, I really don't remember, but what is the condition for the metastability? Is it like lambda 0? Oh, yes, it is actually larger than the, okay, yeah, the, okay.
You get a second minimum?
Yeah.
And then the tunneling, you can tunnel. The lifetime is longer than the age of the universe.
Right. Okay. So the current actually measured values of the top quark and Higgs mass, they tell us that actually we are somewhere in the metastable region. So similarly, this also has importance for the W boson, because for the sake of consistency of the standard model, there are actually certain relations. For in this case, the W mass actually does depend upon the Higgs mass and the top quark mass. So you can basically ask again the question that if your top quark mass, whatever you have measured, how consistent it is with the W mass measurement and all those things. Okay, so that is actually, that information is provided in this plot in this region, for example. So this region is the region which is consistent with the data for the W mass and the top mass at LEP, Tevatron, and the LSC. So how do we actually measure the W mass? So the most precise way of measuring the top mass is that you try to reconstruct it using its decay products. And that's what is actually shown in this plot, that if you reconstruct the top from its decay products, then you are expected to basically get a peak somewhere, and you measure basically its mass and the width. But what is important to mention here that this way of measuring the mass is closer to what is actually known as the pole mass. So if you remember that any parameter that you have in the standard model, you need to basically tell me that in which renormalization scheme you are calculating it, right? So pole mass is something which is related to the on-shell scheme, right? Where you say that your physical mass is the mass which appears in the propagator. So this mass is actually, which we measure, is closely related to the pole mass. But the problem with this pole mass is that for the quarks, this is not actually very accurate. This always will have an accuracy of the lambda QCD, okay? Because quarks are, first of all, they are not free, and due to the strong interaction, you will always basically have an uncertainty which is of the order of lambda QCD. So keeping that in mind, basically you would like to define the mass of the quarks in the MS bar schemes, which is completely perturbative object, and you can predict as precisely as you want given your perturbation theory. So in that case, basically your top quark mass becomes running mass. And these two, as you know, that the different parameters, a parameter calculated in different scheme, actually they are related. So the pole mass is also related to the MS bar mass. But as you can guess, that this relation is not perturbative, because there will be non-perturbative effects because of the strong interaction. So that's all basically I wanted to share. So just to summarize that the top quark has a very special role in the standard model because of its very strong, very large mass and very strong coupling with the Higgs boson. And we need to know this quantity very precisely to make precise prediction for observables, which include, for example, charge asymmetry, which include the observation related to the spin correlation. And once we basically know this quantity very precisely, we can probe the beyond the standard model physics utilizing various observables. I'm open for the question now.